Hello everyone, welcome again to my channel. So today we are going to discuss the medium level LeetCode problem, and the problem is find eventual safe state. So I will just try to explain what is the ask in the problem, and then we will discuss some of the examples here, and then we will try to understand how we can think for the solution. Okay, so in this one, first of all, this is a graph problem, and I personally really like the problem they have put it in. So another thing is, this is a directed graph. We are given a directed graph which has the n nodes starting from 0 to n minus 1, and what we are given is we are given a graph as an integer array which contains the nodes from A to B, source to destination. And there is a concept they have mentioned, that is a terminal node. So terminal node is nothing but which has the outgoing edges to 0. It means there is no outgoing edge from that particular node. And another is safe node. So what is the safe node? So if there is a node which has a path from that particular node to the terminal node, so that can also, like, you can reach to the terminal node, then that node is considered as a safe node. So what we have to do is we have to return an array containing all the safe nodes in the graph. Okay, and the answer should be sorted in a ascending order. Now first of all, we will try to take a look at the example, and these are the constraints, some of the constraints given. So let's take an example. So this is the graph input array we have given. So for this one, this is a 0 based index, and this is and in this one, for 0 you can reach to the 1 as well as 2. So there is outgoing edge from 0 to 1 as well as to 2. Similarly, for one index there is outgoing edge to node 2 and 3. So you can see this is a 2 and this is 3. Similarly, for third node, fourth node, and so on. Now if you look at here, the fifth node and sixth node does not have any edge. So those are called as a terminal node, because as we have seen, a terminal node if there is no outgoing edge. So of course these are the safe nodes indeed. Okay, because terminal nodes can be the safe node because there is no outgoing edge, or even though, like, if there is a node and which comes to these terminal nodes, those nodes are also called as a safe node or terminal node. Now if we start from the 0, and then if we try to see all the nodes, if we try to see whether the particular node is a safe node or not. So if you look at the 0, from 0 we can see there is outgoing edge to the 1, from 1 there is outgoing edge to 2, and from 2 there is outgoing edge to 5, but from 1 there is also an outgoing edge to the 3, and from 3 again it goes back to 0. So if you see, this forms a cycle. So that's why 0 cannot be a safe node or a safe node. So we can eliminate this. Now if you go to 1, same story. From 1 you can go to 3, 3 to 0, and 0 to again 1. So again 1 is discarded. From 2 there is only one edge which goes to the 5, that is a terminal node. So you can put this 2 in the list. So that's why 2 is, you can see in the output. Then from 3, as we said, 3 to 0, 0 to 1, and again through 3. So 3 is also discarded. For 4 there is only one outgoing edge, you can reach to the 5, and 5, 6, indeed those are the terminal nodes. So that's why they should be a part of that safe node list. So that's why the output is 2, 4, 5, 6. Similarly, you can take a look at the example number 2 and you will get an idea. Now to solve this problem, one thing we can understand is there are few inputs given. So first of all, it is a directed graph, and one thing we can understand here, somehow we need to play with the in degrees, or you can say out degrees of the node. Now whenever we talk about the in degrees or the out degrees, one thing we can see is it is part of the topological sort. Okay, so topological sort basically works with the degrees. So it can be in degree or out degree. Okay, so this is a one standard algorithm you can use when problem tries to focus mainly on the in degrees or the degrees of the node. Okay, now that is the first thing. So let's try to think it in terms of the topological sort. Now if you don't know about the topological sort, you can check out the articles. So I would prefer you can check out the articles on the Geeks for Geeks. They have a very good blog written over there. So in the topological sort, what we do is, first of all, we create a adjacency matrix. So so let's try to write down the step. So in the any graph problem, the first part is the adjacency list that we have to prepare. Okay, so that is the first thing. Now once that is done, second thing what we have to do is, once the adjacency list is prepared, then we have to calculate the in degrees. However, when we talk about the topological sort, we have to put the adjacency, we have to form the adjacency list in a such a way that instead of 0 to 1, we will if there is a edge from 0 to 1, we will put a opposite link. So from 1 to 0, we will try to add a link. So that way we have to reverse this whole chaining or the linkages and form the adjacency list. Once that is done, the second step we have to calculate is calculate the in degrees of the vertices. So for each of the vertices we have to calculate the in degree. Okay, that is the step number 2. Once that is done, so once we calculate the in degrees, so first of all I am just trying to explain the topological sort algorithm, and then we will try to look at the code and see how it comes with a solution. Okay, once that is done, then we have to put the vertices which are in the queue, which are having the in degree is equal to, so I will, for simplicity, I will just mark id for the in degrees. Okay, so whatever vertices which are having the in degrees as a 0, so those can be a part of this queue. So initially if you see here, 5 and 6 which are having the in degrees is equal to 0, because here we will map the reverse link from 5 to 4 and 5 to 2 instead of 2 to 5 and 4 to 5. So 5 and 6 will be initially would be a part of the queue. Okay, so just look at this again. Then iterate through this queue and try to, what we have to do is, we have to iterate through this queue and we have to take this element out. So 5 is out now. Now then we have to check what are the edges we have from the 5 to 2. 5 vertices 5. So there is one edge which goes to the 4 and there is another edge which goes to the 2. Okay. Now here 5 is popped out of the queue. Then we have this 4 and 2. So initially it goes to the 4. Then whenever one thing we have to do is, whenever one more thing I forgot here, we have to maintain the, or maybe it's not necessary actually, anyways we are maintaining the in degrees for each of the vertices in this step number 2. So whenever we find a node from this particular node which is having the in degree, so we have to eliminate that one, because we are visiting this. As soon as you visit it, you have to reduce its in degree by 1, because you have to cut this link now. So in degree for the 4 was 1, so now it will reduce to 0. Again, as soon as the in degree is reduced, you have to put this into the queue. Okay, so this will go into the queue. So your 5 is out, but now your 4 is added in the queue. Okay, then, or maybe I can put it here. So 5 is out and now we have 4 and 6. Similarly for 2, again you need to discard this link, and but for initially for in degree for 2 is there are 3 outgoing edges from the in degree is for this 2 is 3, but now it is reduced by 1. So that's why this will become for 2 there is a in degree 1 only, because there is a only outgoing edge from 5 to 2, and when we reverse it, incoming edge is only 1 from 5 to 2. So for in degree of 2 gets reduced to 0. So you have to put this 2 in the list. So again 2 is put in the list. Then we traverse, then again we come back to the queue and we popped out the element. So 6 is eliminated, but 6 doesn't have any node, so we don't need to do this. Similarly 4 is eliminated, but again 4 there is no outgoing edge, so we don't need to worry about it. Similarly for 2 there is again when we go to this one 0, and again from 1, but for these this is a both of them containing the integers as a 2, for integer as a 2 for 1 as well as 0. So even though if you reduce it by 1, so it will becomes 1, and for this also it becomes 1. So finally if you look at the integers of the array, so you will get something like this. So starting from 0, 1, 2, 3, 4, 5 and 6. So for anyways for 6 and 5 it is the 0 0, again for 2 and 4 we got the 0 0 degree, and but for the other elements we will have a something called the integer as a something like this. And finally we have to just go through this integers array. Okay, so this integers array we have to go here and check. So wherever you find the integer as a 0, you have to put it into the list, that is your output. So here this is the output array, so 2, 4, 5, 6 which are having the integer as 0, and that's it, your answer. So now if you look at the solution here, let's quickly look at the solution. So what I have done is, first of all I have taken a graph size, then I have created a queue, then here I am preparing the adjacency list of lists, then I have created the integer array, and this is the output list array, output list. As I said, first we have to prepare the adjacency list here in a reverse order. Okay, that is a typical standard for the topological sort. Then we are calculating the integers for each of the vertices from the adjacency list. So whenever you see if there are whatever the outgoing edges, so from that node, so you are just putting that as an integer of that vertices. Then what we have to do is, whatever vertices which are having the integer as a 0, we are simply putting it into the queue. Then we are iterating through the queue. So in the queue we are polling the top element, or the we are polling the element here, and for that particular element we are trying to iterate through the adjacency list. So whatever nodes which are adjacent to that node, and once we visit that node we are reducing the integer by 0, and as soon as if we find the integer is 0, again we are adding that element into the queue. So similar, this will iterate through the loads as long as we get the integer as a 0 or the non-empty queue. Once this is exhausted, then finally we are iterating through the integer array, and whatever nodes which are having integer as a 0, we are putting it into the output list, and we are returning that output list. That's it. So that's the idea about the topological sort, and you can call it as a Kahn's algorithm as well. So that's the solution of this one, and I will post this solution link, I mean the GitHub link, in the solution or the description of this video. Yeah, okay.